and break everything. Great. Hopefully the Zoom people can see the screen. I did the same thing I did last time, which also failed, but hope for the best here. Okay. If it doesn't, start raising your hand or add comments or something. Okay. So welcome back to part 2 of PCA, Principal Component Analysis. Last lecture was a lot of fun for me. I don't know if it was as much fun for everyone else because there was a little bit more math than I probably should have put in a lecture. We're going to stick with it, but today I'm going to try to recap and make that math seem a little bit less complicated. And then we'll spend hopefully most of today making pretty plots in 3 dimensions and visualizing politics and fashion. So it should be a fun lecture. I said that last time too. All right, so quick refresh of why we're doing principal component analysis, because we want to work with high dimensional data. And when we have high dimensional data, and I'm going to break my pen. When we have high dimensional data, that means we have many columns, and working with data with many columns is hard. You could plot every pair of columns, which could take a while if you have hundreds of columns. You could try to do the things I did in the previous lecture where I add color and 3 dimensions and stuff, but at some point, many columns is just hard. So for visualization and for some modeling situations, we'll want to make our data smaller with fewer columns. Not less data, but less columns. Okay. Part of why we can do that is the world often isn't as high dimensional as the data would suggest. I measured all of these things, but I'm really just measuring something about a person or a shape or a product. And there's some intrinsic low dimensional space. Sometimes we use the word manifold, living on a manifold. Some low dimensional space in which our data lives. Wouldn't it be nice if we could have that? Right? So we measured all this stuff, but I just want the true basic dimensions of my data. This is dimensionality reduction. Goal is to find something like that, to take our high dimensional data and find a smaller set of new features, columns that approximately capture this information. So that was what we were trying to do. And then we, or at least I, got lost in some math in the last lecture. I will try to recover from that in a moment and work through what was going on with our matrix factorization example. Okay, just pictorially. This guy go away. Pictorially, we had this idea of, this is my data in 3 dimensions. You can't tell because it's on a screen, but believe me, that's 3-dimensional data. And there's this plane that the data sort of kind of wants to live on. And if I could just get that plane and where these data points live, I could plot it in 2 dimensions and make a better picture. And that is basically pictorially what we're going to do today. And we're actually going to do that with real data. But I said matrix factorization. So in the last lecture, I said, well, we have this big data set. That's our X. That's D is big, a lot of dimensions. We have a lot more data, but we have a lot of dimensions up here. Wouldn't it be nice if we could break this into a smaller table, which had just K dimensions, that when it's treated as a matrix, Z, if I multiply it by W, this magic matrix, which we have yet to figure out how to build, if I just did that, I would get back my original data, or something approximately like the original data. Wouldn't that be nice? Okay, so that is what I want. And I really just want the Z so I can make pretty pictures. And principal component analysis is about finding this W. And in finding this W, I will also find this Z. How do we do it? Theme in this class. It's called principles and techniques. We do a lot of techniques. We have some principles too. Loss. Minimizing some loss for some model. That's a lot of machine learning, a lot of AI, a lot of statistics. What am I trying to do? I'm trying to do something that reflects my data. How much does it reflect it? Loss. Was something the model? And I just want it to be close to my data. So here's my X's. This is my row of X. The animation here. It's a row of X. And then here is a row of my ZIs, a row of my things that I wish I had. And I multiply it by this matrix W. And that gives me an error. So I have my centered data, my principal components, which we don't know how to build yet, and this rows of Z, my latent vectors. Again, the things I want to plot. And I want to minimize the difference between when I do this to reconstruct one of these. I want to minimize that error. And we picked an error we all know well, the L2, the squared error. There are many ways to do this. There are many such matrices. I can scale this by A, and I can scale this by 1 minus A. I can do different variations of that scaling. So we needed to pick something to make this unique. And so we're going to, or at least partially unique, we're going to pick our W to be an orthonormal matrix. You can think of that as the rows of W have magnitude 1. That's part of it. And that any row against the inner product of this row and this row, which is, if I take the inner product of these two rows here and here, should be 0. They're normal, perpendicular. If I dot product things that are perpendicular, I get 0. Okay. So when I do this matrix multiply, I get 1s on the diagonal because that's dot producting with myself. Zoop, zoop. This one here. But anything off diagonal, this one, and let's say this one, that's going to be 0. Okay. Orthonormal. That's my goal. We have an objective. We even had a constraint. And this is where I got excited. So I then can minimize this objective with this constraint. Step 1, we showed, and I will not show again. This was actually algebra that you probably should be able to do. We showed that Z is minimized, that loss is minimized when we choose Z equal to X inner product with W transpose. Dot product, take the matrix X, and this is projected onto W transpose, or onto W. Here. So great. If you know W, you know how to get Z. We don't know how to get W yet. That's sort of where we got lost last time. It's like, okay, we figured out Z. We kept going. Let's take derivatives and figure out W. So we now know that Z is this. We can plug that back into the equation that is not on this slide or in this lecture. And we started doing this fun stuff. I added Lagrangian multipliers. So cool. Unfortunately, out of scope for data 100, because you guys don't know what that is. Kind of know what it is. I gave you a hint of it. You'll see it again in some other point in your life. And we did that to get this orthonormality constraint in our objective, because we have a constraint. Then we took derivatives with respect to W. It's like, oh, that's fun too. It looked like regular calculus, but technically I did vector calculus because my W's weren't scalars, they were vectors. You could squint and go, yeah, that makes sense. You had W times W and you made that 2W. Some transposes and stuff, but it worked out. This is also out of scope for data 100. It's a bummer. So you do not need to actually know how to do vector calculus, but you can kind of see what I did in that process. We took derivatives and then we set them equal to 0. And I was so excited, I flashed up this picture. Whoa. And everyone clapped, except no one clapped because nobody understood what I was doing here. What was I doing here? Does anyone remember what I was doing here? Someone remembers what I was doing here. That's good. Should do a poll. Okay. So we should go back to this. This equation is amazing. First, because it has sigma. What's sigma? What's sigma? I don't know. Okay, that's a bummer. Sigma is the standard notation in statistics for a covariance matrix. Sigma is if we had centered our data, and we did. If I took my data and did X transpose X, that's sigma. It's the covariance of my data. You might remember covariance being something that looks like X minus mu transpose X minus mu. Except we set mu is 0. So we get X transpose X. And this is, again, what we said was sigma in the past. Covariance. I believe I taught that in this class, so I know you know it. OK. So that's cool. Covariance matrix, very exciting. I guess this is on the slide, so when I asked you that question, it was less fun. What is this? Eigenvalue equation. Super exciting. Whenever you see an equation like this, matrix times vector equals scalar times vector, that same vector, this is an eigenvalue equation. And that means these things have names. We have this thing is called an eigenvalue. And this thing here is called an eigenvector. Those of you who do know what's going on are like, Joey, why is there a transpose here? Okay, so normally when you see an eigenvector equation, it looks something like Ax equals lambda x. Unfortunately, due to my notation, W here is a row vector, so I had to transpose it. So it looks like a column vector. For those of you who were not confused by that, please remain not confused by that. That's matrix times vector equals scalar times that same vector. So that's super exciting because we have machinery to find these things. And if we know that the answer, the thing that minimizes our loss, looks like that, we know how to solve for it. And as we recall before, we have this extra constraint, which is fine because our machinery is going to preserve this constraint as well, that we want this to be an orthonormal or row orthonormal matrix. Yes? This equation. Great question. Why is covariance so exciting in this equation? Why should you have all been clapping when this came up? Well, I said the first way to show PCA is finding the direction of maximum variance. Covariance matrix is measuring that variability, right? It's measuring the variability across dimensions and then along each dimension. So the thing that that solves this is also going to be directions of maximum variance. If I choose the eigenvectors with the largest eigenvalues. It's related to the Rayleigh coefficient, which again, out of scope for this class, so ignore I just said that. Okay. How exciting. You're all now very excited by this, right? Yes, I'll just assume so and move on. Okay, so now what do we got? This is, I think, we left off last time. Principal components are eigenvectors with the largest eigenvalue of our covariance matrix. That is the directions that maximize variance, right? Minimize loss, maximize variance, same thing. We can construct the latent factors of the Z matrix by projecting the centered X on these principal components, which we know are now eigenvectors, and we're going to use some magic in a moment to find those eigenvectors. That's how we get our Z's. Project. So now we know our Z's. We know how to get our W's. All centered, principal components. And by the way, these are called the principal components. Unfortunately, in previous versions of this class, these were called principal components. I have made that mistake in the past before, but the correct definition of principal components are these guys here. And these are just factors. Some of the lectures that we will link to from other faculty elsewhere also make this mistake. It is a common point of confusion. If someone calls this principal components, don't get too upset with them. Just another way of thinking about it. These are technically called latent vectors. Sometimes they're called scores. I'll just say X project onto principal components, but these here are my principal components, these guys right here. Columns of this thing. Rows of W, columns of W transpose. Confused? That's okay. We're going to keep doing this. We'll get some more examples. So how do we compute the eigenvectors of the covariance matrix? And that brings us to the last mathy part of this lecture, which, having learned my lesson on Tuesday, I will try to make less mathy today. But it is a very cool concept. The singular value decomposition. So these really big ideas in linear algebra. It's a very important concept. We assume you've taken some linear algebra or are taking it now. So hopefully some of these vector ideas are starting to make sense or will make sense in the next week or two. I will not explain SVD. I really wanted to, but we don't have time for it and you'd be confused. And I'm not going to prove stuff about SVD, except I might prove why it's related to PCA, because we can do that now. We have the tools. There's this E16 lecture notes, which are awesome. So if you really want to go learn everything about SVD, you can check those out. So it's a pretty in-depth study of the properties of SVD in the various flavors. But not today. Today, I will just tell you, SVD is a piece of magic machinery that takes my matrix X and factors it into three matrices, U, S, and V transpose, three matrices. I will say just notationally, I am going to use the letter S here. If you see anyone else's lecture, guess what letter they use here? Which is very confusing because sigma means covariance and not singular values. Interestingly, they are very related, which we'll show in a moment. But I'm going to call this letter, this is the letter S. I don't speak Greek, and so we'll just stick with simple letters here. So U, S, and V. Let's talk about these magic matrices. U is going to be a the columns of U are orthonormal. So they're unit length, and they're orthogonal. And this is cool. The columns of U are the eigenvectors of X transpose. We don't need that, but it's a cool fact. Now you know that. S is a diagonal matrix that is D by D, so that my columns by number of columns. And along the diagonal are the things called singular values, from which the singular value decomposition, or SVD, gets its name. And they are ordered largest to smallest. And if our matrix is rank R, then there'll be R non-zero singular values. So if our matrix is lower rank than the dimensions of our data, we might actually not have zeros along the entire, or non-zero entries along the entire diagonal. So maybe I'll just draw a quick picture. So this is my D by D matrix. See an example in a moment. And if my thing is rank R, then I'll have ones along here, and then maybe it stops here. This is R. Here is R. And then it'll be zeros all the way around here. These squared are my eigenvalues. Well, let's get to this next piece here. We'll come back to that. So next we have V. V is exciting. So V, the columns of V, so this is V transpose. The columns of V are also orthonormal. That's something we wanted. And this is the big reveal. The columns of V are the eigenvectors of X transpose X. So call some magic function. Spits out 3 matrices. I got matrix V, and I'm good to go. It would have been a much easier way to present this entire lecture, but now you have the math behind it, and you know why it's related to this principal component, loss minimization problem. Here's an example. So we have a table of rectangles width, height, area, and perimeter. What's the rank of that? Oh, no. Don't look. OK, we get the answer, I guess. Why is it rank 3? Width, height, perimeter, and area. Think about it. We did this in the last lecture. Perimeter is a function of the width and the height, right? 2 times width plus 2 times height. Perimeter, a rectangle. So it's rank 3, which means that I'm going to get a matrix U, which I said would be N by D. These are just some numbers. I get a matrix S, which is D by D. It's mostly 0. It's all zeros here. 0. So it's diagonal. And it's also 0 here because it's rank deficient. X was not full rank. Okay, so it's only rank 3. And I get VT. And that's the one I was so excited about. The rows of this matrix are my principal components, things I want to project onto. So now we can make pretty pictures. So yes, this was rank 3. Okay. So the last mathematical step is, how do I get my principal components for SVD? I just told you, but just once more to see it happen. I'm saying that X is equal to US V transpose. This is just a fact. My computer program gave me US and V transpose. If sigma is my covariance matrix, I wanted the eigenvectors of that. Well, sigma is equal to X transpose X, as I've centered my data. If I just plug this in here and here, this is X transpose times X. And the transpose of things in parentheses, how do I deal with that? So the transpose of this is equal to, I reverse the ordering, so I'll read it backwards. And I take the transpose of each thing. So this is V transpose transpose, that's just V, S transpose, and U transpose. And that's what I got here. Clear my slide for a second. And something neat happens. This was an assumption that we had about U. U transpose U is the identity matrix, so that's just 1. So we get sigma equals V S squared, just for simplicity of notation, times V transpose. If you're curious, S squared is just the square of the diagonal elements of S. If I right multiply, so I'm going to put a V on both sides here, you get sigma V equals V S squared times V transpose times V. What's going to happen? What do we know about this? What's V transpose V? 1. Boom. It's the identity matrix. So what do we have now? Everyone's super excited again, standing ovation. Yes, what is that? An eigenvalue equation. But here I have a bunch of vectors. Zoop, zoop, zoop. And here I have a bunch of vectors here. So it's a bunch of eigens, an eigenvalue system, a bunch of eigenequations. So this tells me that V, which I already told you in the earlier slide, is the eigenvectors of sigma, which was our end goal. So a bunch of math to prove to you that I've got my eigenvectors. Okay, so V is my principal components I showed you in math. You do not really need to know all this math, but it'll help you in your future careers, so I showed you anyways. Out of the way. And this means that S squared, so the principal components squared, are the eigenvalues of sigma. Yep. Yeah, so this is a notational thing. S transpose S, I've written as S squared. You could keep it like this. S transpose S is still a diagonal matrix with sigma 1 squared, sigma, oh no. I said I wouldn't use sigma. Okay, it's hard. S transpose S equals, I said S squared, which is equal to a diagonal matrix with S1 squared, S2 squared, and so on. So it's a square of the S's. Just easier to see. You could leave it at S transpose S. That's fine too. These, when I have a diagonal, like a diagonal matrix right on the right of this, is just scaling each of the columns of this matrix V by one of the corresponding sigmas. S is a diagonal matrix. So diagonal matrix times diagonal matrix. You square the elements. Okay. Good questions. One thing I will say, again, you don't need to know all this. You're co-taking a linear algebra class, but it is helpful to see all this. It'll hopefully make the linear algebra class maybe make a little more sense. And again, when you go further and do like 189, you will need to know all this stuff. So practice. Okay, now we're getting redundant here. How to do it. So now I've got my V. This is in Python. And I can do this little V subscripting trick. What is that doing? That's saying I want all the rows of V, and I want just the first K columns. So maybe I should make this K is, K is here. Yeah, I want the first K columns. So this is shorter than D. So D is this long, but I'm only taking a little bit of it. So I'm leaving off some of the other columns here. That's a bummer. Some other columns here that I didn't get. This would have been D over here. It's D. So I'm taking just the first K columns. This bigger V matrix. Okay. So this is the Python notation, which we'll use in a moment anyways. So I'll show you how that actually works. So that's all I got to do. Call SVD, grab that matrix V, and multiply it by X. And I now have Z, so I can make pretty pictures of my data in low dimensions. And in practice, I will typically use K equals 2. And for this lecture, for your entertainment, we will also do K equals 3 dimensions. Okay. Here's a way to compute Z, kind of a fun side. So I told you Z equals XV. We just did that. We even showed that a while ago. Remember I said X is this thing up here. So I can go ahead and put that right there. And we know that V transpose V is 1. This is 1, the identity matrix, which means that Z is also U times S. So many ways to make Z. Pick your favorite. Doesn't really matter. All right, so let's actually do it. So here's my matrix X. There you go. Here's my matrix V right here. Big matrix. But I just want the first two principal components of V. So I'm just going to pull these two columns, PC1, PC2, and I multiply it by X, and I get Z. It's me Z right here. That's it. PCA with SVD. I said you could do it more than one way. Here's the other way to do it. Here's my matrix U that SVD spit out. Some eigenvectors of XX transpose. That's weird. But I take the first two columns of it, take the first two columns, two rows of S, multiply them together, and I get the exact same Z again. There are two ways to compute the answer. And I've said this a bunch, but I'll say it once more. If I take just a few columns, I'm going to approximate the underlying x. And what do I mean by that? So I've built my z as an approximation, low dimensional representation. I can multiply that thing again by v transpose, which I have from my library. X v transpose. This is also going to be 1. So I get, oh, sorry. Typo here. I get x, correct. Because this is 1, I get back USB. Okay. Let's actually go through an example now. How to transform, let me give this one picture. I probably should have started with this picture at the beginning of lecture, but we'll do it once more. For those who are still a little bit lost, here's the end story of what we do. We have data in 2 dimensions. So this is my cloud of data over here in 2 dimensions. I am going to do first step of PCA is center my data. Just subtract off the mean, so it's now going to the origin down here, step 1. Step 2, I run SVD. I get those eigenvectors, and I project onto them. And that's going to rotate my data so it's aligned along the 2 principal component dimensions. This data started out in 2D, and it ended up in 2D, so I didn't really accomplish much. But if you'll notice, if I had thrown away this dimension and I just had kept this dimension, I would have had most of the interestingness about my data. So I have taken my data from 2D. If I drop this dimension, it looks like all my data would look like this along this line. That kind of captures where the data is. It doesn't capture this information where it deviates from the line, but it captures where it is on this axis, principal component 1, which is where most of the interesting stuff is happening, where most of the spread is. All right. We can go through all this. Actually, 2 points I want to bring out. So once I run PCA, we already said that the things are orthogonal. The columns of view are orthogonal. Our data is going to be aligned along these axes. I want to say, yeah, principal components are linear combinations. So the principal components that we build are linear combinations of the original column space. So they're still a subspace of the original column space of my data. I think I want to also say something about the covariance, but we'll do that in a second. All right, actually, let's go through a demo. So that's sort of the end of most of the math for today. Are there any questions at this point on the math? How are people doing on Zoom? You know, weird. People are doing good. Okay, we'll go with that. Let's do some code. We're not going to start with fashion. Second. Outputs. Okay, here we go. So I have a notebook, which I'm going to pull in my rectangle data. No, I don't want this one. I want this one. Votes. Here we go. Notebook, and pull in my rectangle data. So I have width, height, and area. I center my data, step 1. So I take the rectangle data and I subtract off the mean. That's the mean of all the rows. So take the mean across the rows. So I'll have the mean width, mean height, and mean area, mean perimeter. Something that I didn't talk about that is pretty common is I will subtract off the mean. In some cases, I'll also want to standardize my data. That is, I want to make sure that the variance of the original dimensions are about the same. Why do I want to do that? Well, if you happen to have a dimension that was like square of another dimension, let's say area, then the principal component analysis go, wow, everything's really varying along that dimension. So that must be a really important dimension. And it may not be. It just happens to have weird units, squared units. So when you have data that has weird units, like squared, cubes, and things are like billions of dollars and then the height of the person, you might want to scale those things so the original dimensions, before you do all the magic, are about the same order of magnitude of variance. So you don't just overfixate on that, billions because the numbers are big. So I'm going to divide by the standard deviation. It's another technique to do. I'll show you what happens when we first start with x, just subtracting off the mean. So x is the centered data, as I said in lecture. Here's how to do SVD. We could have spent half a lecture on this whole topic if I just jumped here. So I'm going to say NumPy is linear algorithms library, SVD function of x, and I don't need the full matrices. If I was ranked efficient, you can get additional eigenvectors even when the eigenvalues are 0. Don't worry about that. Just say full matrices is false, save some compute. So what do I get? I said before the shape of U is going to be n. My data was n 100 by 4 dimensions. S is this diagonal matrix, which is just 4. That's weird. Come back to that in a second. And V T is 4 by 4. These are my principal components. So S is written as a list, as a one-dimensional array, which is just diagonal elements. Why waste storage storing all these zeros? But if you want to make it a diagonal matrix, you can just convert it to a diagonal matrix instead of just the eigenvalues along the diagonal. You'll notice that we said this was rank 3. There's a non-zero entry on the 4th principal component. Why? Well, it's basically 0, 10 to the negative 15. So we'll just call that, is it close to 0? Yes, it is close to 0. NumPy has a function to test that. Floating point math is imperfect, so you'll get things that are basically 0, but not actually 0. So we can deal with that. If we round to 5 decimal points, and I look at just S, the original vector, these are the diagonal elements, you'll see that it is in fact 0. It is 0, again, because that matrix is rank 3, not rank 4, even though it has 4 dimensions. Yeah. Are those numbers sorted? Yes. And how are they sorted? Good question. So remember, they're sorted from the largest to smallest principal singular value, which is the largest to smallest of the square root of the eigenvalues, or if I square them, the eigenvalues, because remember S squared is the eigenvalues. That's important because well, I'll show you in a second. It's going to tell me something. So we have our diagonal elements. I made it prettier, rounded and stuff. Let's look at this. This is S squared divided by N. So this, and I'll come back to a moment in slides, this is the variance along each principal component dimension. And that's very useful because now I can actually calculate, if I project my data, what will the new variance be in each of these dimensions? And the variance of the first dimension is huge. Why is the variance of the first dimension huge? The first principal component explains most of the variability in my data. We'll make some plots of this in a moment. Just for fun, I'll also do SVD of my standardized data, where I not only centered it, but I divided by the standard deviation of each of the columns to make it so that area doesn't get all this extra attention, because it just happens to be a bigger kind of number. And then we see this a little bit different, right? So here, there's one massive principal component that really just explains everything you need to know about rectangles. Now there's one that explains a lot, and then two that explains a fair amount, and then the rest, not much, right? Why is that? Why do you need 2 numbers for a rectangle? If these were squares, how many numbers would you think I need? 1. Why do rectangles need 2? There's intrinsic dimension of a rectangle is 2? That's absurd. Where's it? Maybe we should draw a rectangle. Cannot, yep, let's do that. Command 1. What does a rectangle look like for those who are less familiar? With my rectangle, there are 2 numbers. Height, width, right? If these were squares, I could have gotten away with just 1 intrinsic dimension. How many dimensions here? Height, height, right? Squares, everything's equal. Rectangles, you got 2 numbers. So we kind of expected, if we were thinking carefully about it, that the intrinsic dimension of this data is 2. Okay, well, jumping ahead to my eigenvalue discussion. Okay, so step 3, we construct our approximation. I said there was 2 ways to do it. I've computed U, and I have my diagonal matrix S. I take all the rows, but the first 2 columns of U, and then just the 2 diagonal elements of S, and I multiply them together, and Z. I get my Z, my projection of my data on the principal components, sometimes called latent vectors, latent factors. This is the stuff I want to plot, and we will plot today, soon. Okay, let's also project onto my standardized version. So here I'm doing X times V this time. So I'm taking my X that's standardized, and I'm multiplying it by my VT, right? So I'm taking all of my X, and I'm taking all the rows of V transpose transpose, that's confusing. V transpose transpose, also known as V, and I just want the first two columns. All the rows, just the first two columns. And it's the same thing. Why is it the same thing? Because when I computed STD a moment ago, I did it for the standardized data. So these are the Z for my standardized data, and this is the Z again for the standardized data, and these are identical methods to produce the same result. Plot time. What is this going to look like? Those are my rectangles on 2 dimensions. It's good. Don't get much from this picture. In a moment, you're going to get blown away by pictures, but this one I don't get a whole lot. Just for completeness, we can also do this entire calculation by calling one function PCA. So I get a PCA, and I just want 2 principal components. And I do PCA fit transform on whatever data I have, and magic, I get another embedding. Right? So all of that math could have been reduced to this many characters, and we could just skip the whole week. It's kind of a bummer. All right, here's my Z again for this one. Let's actually look at something cool. So if I look at my Z, my data projected on to the principal components, there's one last thing I want you to know, and that is, to make this easier to see, np.round. Just like 3, that's good. That it's diagonal. It's important to know. It's one thing I wanted to say earlier in my slides. Once I've done all of this PCA magic, I've made the covariance matrix of my data diagonal. So I've rotated it so it is diagonal. So I've made the dimensions independent. That's a strong statement. I've made it the covariance 0 across the diagonals, or across the off diagonals here. All right. A little more pictures. So let's do this picture. So I'm going to try to recover my data, and this is what it looks like. So the blue data is the original rectangles. Make this easier to see. The blue data is the original data points where I had width, height, and area. I've ignored perimeter because that's redundant. So width, height, and area. It's on that blue kind of Pringle-shaped curve. And the red dots are my approximation. I've projected onto that plane that kind of more or less fits to that blue curve thing. And so if I go to reconstruct my data after bringing it down to 2 dimensions, I lose a little bit of information, right? Because I'm doing a linear transformation. If I want to preserve information about area, I can't do that with just a linear transformation. So it's not perfect. All right. Questions for your turn to lecture? Yeah. Great. So let me do this again. I made a very strong statement. With the rectangle, it is true. There are only 2 things you need to know, height and width. Problem, PCA is a linear operation. So how do you get area from height and width? Height plus width is not area, right? So I actually do need 3 dimensions if I want to recover area, if I'm going to use PCA. We will not cover in this class, but there are methods that can actually find this, again, 2-dimensional manifold, this blue curvy thing. It's still a 2-dimensional thing, but it's bent. So PCA alone is going to be a lossy projection. It's going to find a lower dimensional representation that captures a lot of what is important about a rectangle. There's really just kind of 2 numbers, but not enough to recover the data completely, because area is not something that I can recover with linear operations. So I am losing information. And we saw that because even when I did this SVD decomposition, where's the numbers? Go, 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 go. Where's the numbers? Oh, I went too far. V of S. Here we go. The last singular value was not 0. I standardized my data, but there's still information there in that last dimension. I can't recover the full data with just 2 dimensions. But I'm pretty close because area, at least when these things are small, is pretty close to a linear approximation of width and height. Okay, so if I made this data bigger, I had giant rectangles, I'd have more and more loss, more and more error. Are there questions? Questions? We want to get to pictures. Let's do it. All right, so I want to finish by talking about some of this discussion on total variance. So in our original data, we had this notion of the sum of the variances of all the columns. So I take the variance of each column, and I get a number, and I can sum these up, and I get this total variance. Right? The whole goal here was to try to find a new set of dimensions that has as much of that variance as possible. All right, so the way to compute the variance of each of my new dimensions when I've projected on these singular values, or onto these principal components, is to take the ith singular value, just 197.4, that's the singular value for the first principal component, square it, because remember, it's s squared to get the variance, the singular values of the covariance matrix. And I need to divide by n, because remember, covariance matrix is scaled by 1 over n. It's just not, I guess I lied earlier. It's 1 over n times x transpose x. You just kind of ignore this in our optimization, but you do need that 1 over n if you want to compute the variance. So bring it back. Right, 1 over n times x transpose x. We bring back our n. And this right here, this calculation, the singular value squared divided by n is the variance of that column of z of that projection onto the first principal component. Which is great because now I can see how much of the variance is explained by just using one of the principal components or using two of the principal components. And I can even make a plot, which I think is on my next slide. Okay. One more plot to discuss before we get back to plotting. So once I've found the right number of dimensions, which I haven't told you how to do, oops, I should do it now. Did I arrange this? Okay. Yeah, we'll just do this and we'll go back to the sliders in a second. I can now plot these variance numbers for each of my principal components, and I make something called a scree plot. And the idea here is if we look at this plot, most of my data seems to be here. I don't maybe need these. I certainly don't need these. These all look kind of, they don't explain much. This explains a little bit. So maybe two principal components is enough. If my plot looks something more like, it'll look like something like this. And maybe it goes like that. Then maybe I need three principal components to represent my data. Right? So this is done pictorially. It's not really a science, more of an art, looking at the elbow in this plot and trying to find what's the thing on the left of the elbow. What are the number of principal components I need to capture most of the variance in my data? It's called a scree plot, which until a week ago I didn't realize was actually related to a geological formation. This is called a scree on the side of a mountain. It's named because it looks like the side of a mountain. Scree plot. Look at Slidos. Okay, so we talked about computing these. And then the last thing that we're about to make some pictures of is once we have our three-dimensional data, we project it, and we already did one of these, project it into a lower dimensional, typically 2, so it's a 2D space. We can start to visualize our data. We'll often attach attributes as color so we can see clusters and the behavior of our data in some lower dimensional visualization. Okay. As I said before, if we need more than two dimensions, it may no longer be a good representation of our data. So we might be omitting a lot of information. Okay, I want to go back. We'll come back to this in a second, this Slido. Let's do some actual fun stuff. All right, so now I get to do the fun part of lecture. We're going to look at complicated data. So I'm going to study congressional House votes in 2020. And so this is the data. So I have the chamber, the session, the roll call, that's the thing that we're voting on, and then the House member, and whether or not they decide to vote, or whether they could vote. Yes, no, abstain, not voting, speaker, and so on. This for all, I think all of the 116th, Congress. So we have data for the 116th Congress about how people voted. And I'm going to do principal component analysis. What do you think I'm going to find? Let's make my data a little more concrete. That'll help a little bit. So I'm going to pivot this data. So now I have the House of Representatives, the congressman, and then I have the vote. So vote on bill 515 or roll call 515 for some bill. I don't know what it was. And then yes, no, 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 yes. Okay, so I have this kind of information. How many dimensions do you think US politics has? Are we a rich, high-dimensional political society or a low-dimensional political society? 2 is a good number because we can plot it. 3 we could also try to plot. Higher than that, it's going to be hard. How would we figure out how many dimensions we really are? Method. Let's try it. So here is a situation where I have 41 columns, 440 individuals on 41 different voting occasions. I can't visualize this data. It's a bunch of ones and zeros. It's a pain. So I'm going to use PCA, try to bring this down to just a 2-dimensional space and see if I place people in this 2-dimensional space, where do they live? Who are their neighbors? First step, got this vote pivot table, which I built here. I'm going to subtract off the mean. More numbers, hard to visualize. Oh, we have a Slido question. Let's do the Slido questions. We haven't done it yet. So I have all these numbers. No, sorry, it's the previous one. Did I break my Slido? Sorry. Let's keep going. I don't think I want to do this Slido yet. One second. I do want to do a Slido, so I make sure you guys get your attendance vote. Look at it. Yeah, my Slido's out of order. It's a bummer. Okay. So I have this 441 members on 41 voting occasions. Let's test our knowledge of SVD. So I want to figure out what is the dimensions of U and S. Slido. Use vote so we can go back to pictures. Okay. Audio is better. Thank you all. I've put the mic a little higher. Maybe that's the problem all along. Embarrassing. Okay. Vote, vote, vote. I want to show you the picture. It's going to blow your mind. Okay. Let's see what we got. Okay. You're getting it. And I will accept this answer too. I'm good with that. Both are basically correct. So the first answer is U, remember, is N by D. And the second matrix S is D by D, except in NumPy, where D by D would be a waste of memory, storing all those zeros. So we just store the diagonal. So it's just this 41. So the correct answer is U. And the pretty much correct answer is, is this one. The pretty much correct answer is this one. Okay. So now we've finished the Slido. I'm just gonna leave this running. I want to show pictures. So at my table, I run SVD pretty quick. And now I'm gonna make a 2D plot. Wow. What do we see? Dots. We see dots. What do these dimensions mean? I don't know. What do these dots mean? I don't know. But the first thing I see, like a cluster of stuff over here, a cluster of stuff over here, and some interesting people over here. Each of these dots is a person in Congress, congressman. Wouldn't it be cool if I had the political affiliation of everyone? I don't want to do this, component scores. I'm going to skip this. All right, no, I won't, because you guys need the Slido. Right, so we're going to do one more Slido. Keep active. So I want to look at the distribution of the, before I dig into what's on those dots, I want to know how many dimensions is the US Congress? If I project their votes into a low dimensional space, I want to find where the variance is explained. So I want to know how to compute the variance ratio for each of the principal components. So what fraction of the variance ratio is expressed by each of the principal components. Okay. It's up here. So is it enough to reduce Congress to 1, 2, 3 dimensions? I want to make that scree plot. In this y-axis, I want to have the ratio, the fraction of the variance, the total variance explained by each of the principal components. Vote. Right, you're close. So S squared over N is what I said earlier if I wanted to compute the variance, but I made this modification here that this time I want a scree plot, because remember, scree is just a shape. I want to know what fraction of the total variance is explained by each of those components. So I want the variance divided by the variance, the total variance. It's my sum of S. Technically, I need to divide each of these by N, but if I divide the numerator and denominator by N, that doesn't do anything, so I get rid of that N. Why would we want to plot this? Because it's easier to look at it. That's 30% of the variance, 20% of the variance, so on, as opposed to trying to read the variance numbers themselves. So it gives me a better sense of what fraction of variance is covered. Put this open. So we can look at our variance. So 80% of the variance is explained by the first principal component. And then 0.05, the ouch. So the US can be reduced to one dimension, or at least our politics seem to be one-dimensional. Make that scree plot. That. There's one dimension that explains the vast majority of the variability in how people vote. So now I can look at higher dimensions. Remember, there's this one that's probably this dimension here going across this way, Z1. It's right here, Z1. Second dimension, some variability here. And if I look this way, the third principal component, there's some variability. Curious what this person's doing up here. Maybe they're interesting on this third dimension. But there's not as much variability. So most of the interesting stuff is happening on this axis right here. So how do we know what is happening? Now the exciting part. I'm going to bring in the political affiliation of each of the voters, each of the members of Congress. Join that with my data. I'm going to bring in a bunch of information at once. And now we can see what's going on, right? We have people who vote blue, or Democrats, people who voted red, Republicans, people who voted green, independents, and then interesting people down here. This is why I do PCA. I can take something as complicated as votes, Congress, reduce it into lower dimension, and start to see interesting patterns. One thing that's happening here, which you can't quite see, is some people vote so identically that there's a bunch of people here. It's called overplotting, when I stack dots, and that this dot is many dots, you can't really tell what's going on. AOC, nice. I would guess she's on the far left here. Yeah, here. That's far. Oh, yeah, no, she's right here, far left. With this plot. It's just a coincidence, by the way, that this organized left to right. Could have taken the reverse eigenvector, but that's what we got. So we spread the US votes, the people on this one Z1 principal component explains a lot of how people vote. And in some sense, that Z1 principal component is their political affiliation, which we sort of might have expected if you follow US politics. As I said, there's people stacked. So to make this a little bit more clear, something you will often do when you make these plots is you'll do some jittering, adding a little bit of noise to each of the dots so that you can see the differences. When you present this in public, you need to say this data has been jittered because you're changing the actual placement. But this is for our visualization purposes. It'll help a lot. So now we can see the cloud of points over here, the cloud of points over here, because the data has been a little bit jittered. You do things like look at the, so I can look at like take away certain groups. A lot more male Republicans. There's one independent. It's embarrassing. Yeah, so this gives us a picture of what's going on. I've done some extra things. So I've encoded the, I think the size as the age of the representatives. So we can see younger, older representatives and stuff on this one plot. So we can still visualize some of the other dimensions, the attributes of the data, but we've taken all that vote, the 41-dimensional vote space, and reduced it to something that we can really see. For fun, we can also look at this in 3 dimensions. I don't think anything else really interesting is happening along this dimension. So there's not much spread. If I look on this dimension, I'm not seeing a whole lot of interesting stuff. Most of the interesting stuff is happening along this dimension, going horizontally, the Z1 jittered, and a little bit of stuff is happening along the Z2 dimension, going this way now. All right. So this data has people who voted different amounts of times, and some people didn't vote that often. They abstained or just weren't present. So we can look at the histogram of voters. We might be curious, I didn't run this analysis, but we could look at like, are the people down here interesting? They happen to be the people here just didn't vote that often. So maybe that's why they're in the middle, just didn't participate in a lot of the votes. They abstained. So we can start to see other patterns as we bring that information into this plot. So this is what you would really do in the real world. You're going to take high-dimensional data, try to bring it down to a few dimensions, visualize maybe 2, 3, maybe pairs of a few of the dimensions at a time. Try to bring other attributes in, seeing things like color, shape to encode other parts of your data. And you're looking for patterns, because this is a big part of EDA. In some cases, you won't have the red and the blue. You'll just have dots. You go, that's interesting. There seems to be a bunch of dots here, a bunch of dots here. Let me start mousing over. Okay, these are all people from states that seem conservative, or these are all states that seem liberal. Let me go see if I can get the political affiliation, and then start to do deeper analysis. So that is how we would use PCA in practice. One more thing we can do is we can look at the actual principal components themselves. So the first principal component is a direction of votes, if you will. It's saying, plot it right here. For 515, it's a negative number. For 520, it's a positive number. Given what we saw in our picture, what do you think this looks like? If I'm a Republican, should I vote yes or no on 520? Republicans are on the right, positive inner product with this vector. Their votes have positive inner product with this vector. This is essentially the vector of what a conservative should vote. And by how much? Right? We believe that that first principal component describes as the dimension of the political spectrum. And we can kind of check that because we have the data. So here is the average votes, yes, no, for each of the parties. And here is my figure from before. If I look at the average votes, it more or less aligns with the average votes of the Republicans. So we could have skipped all this PCA altogether and just said, what's the average vote of a conservative? And project onto that dimension. That's pretty close to what our principal component analysis found. But in the real world, we may not have that label. We just have the data. So we can't do that analysis. Only PCA can reveal this information. Moving along, this is good. We might get to fashion today. All right, one more plot that I don't use often, but I'm just going to bring it up because you might see it. Sometimes I want to understand if I took just 2 principal components, I might want to plot on top of my original cloud of points these vectors. So let's take a look at like one of these vectors, 515. Okay, so this is saying if I take the first principal component and the second principal component, that Z matrix, oof, I messed up just now. Take my data projected onto the first and second principal components, I get that Z matrix. And I look at the correspondence of, actually, no, this is not quite right. Shows. Do I have a piece of math that I can point to for you? Here, this actually does it. So I'm taking my V. If I take my principal component, the first principal component, it's in D dimensions, which means it's a vector in the original voting space. And I can look at the contribution of each of the votes to that vector, right? So if I look at the row, the first row, that's corresponding to vote 515, and has this number in principal component 1 and this number in principal component 2. That's sort of the contribution of that vote to each of those components. I can plot those votes as arrows on this plot. And that gives me a sense of how this vote lived in this space. So these are votes that went liberal. These are votes that went conservative, for example. So one additional kind of visualization you can do is once you have your principal components, you can look at how the original dimensions break down in that space, something called the loadings of each of those original dimensions. I don't typically use this, but you might see this kind of plot in the future. It does tell you a little bit about how each feature contributes to those new dimensions you've created, the two principal components. All right, that is it for votes. In a moment, we'll do fashion, but I want to stop. Are there questions at this point? Correct. So in this example here, I had labels about the political affiliation, and if I were clever, I might have guessed that maybe I could just project onto some dimension depending based on political affiliation. Even still, in this setup, I would have started by running PCA on the votes. I get that cloud of data points. I go, cool, I got a cloud of data points. I do see some clustering. Is there something special about those clusters? And that would bring in the other information I have about the dimensions of those clusters. About the attributes attached to each of those points, like the political affiliation. It might have been those clusters didn't correspond to political affiliation at all. It could have been they corresponded to regions of the country. It happened that in the US, it was political affiliation, but maybe I had to label them by the region of the country. Maybe I have to go grab that information. I don't have it here. I just have the states. But is that state in the Northeast, Southwest? What region is it? So this attachment of labels to the data, that's next Tuesday's lecture. So we'll think about how to assign labels to data when we don't have those. All right. I owe you guys a break. Sorry about that. So take a 2-minute break, stretch, and then we'll do some fashion. All right. It is fashion time. We're doing fashion MNIST. This is a play on a classic data set. We used to play with digits, but they're boring. So we're going to start to reason about clothing, which is less boring than numbers. I'm going to load a very famous data set. This is the fashion MNIST data set. It is typically used for classification for things like logistic regression or design of neural networks. And I'm going to show you how we use PCA to reason about pictures. So we have lots of pictures. Do those pictures live in a lower dimensional space? So you should feel free to follow along. I'm going to sample this data set to work with something a little bit smaller. So I'm going to take, I think, 5,000. Wow, that's a lot. Okay, so I'm going to take 5,000 images from this data set. There's a training and test split. We're not going to worry about any of that today. I'm just going to play with some of these raw images. I'm normalizing and standardizing the data. So I'm going to subtract off the mean and then standardize as well. Okay. Oh, sorry, here I've just normalized. We haven't done standardization. Okay, so here's my images. I've made a data frame where I have a column of images. The images themselves, a picture of this, are 28 by 28 pixels. So each image is a matrix of 28 by 28. And then each entry in that matrix is how bright the pixel is, whether or not it's bright, like a white color, or dark, like a blacker color. So like this, white, black. So these are black and white images, keeps it simple. Okay, so that's the data I have. I'm using some cool visualization stuff. You do not need to understand this code, but if you want to play with this, read the code, it's cool. Yeah, so my data frame is these images. I have a label that would be used for machine learning classification, but I also have the class itself. So image 1 is a dress, image 2 is a coat. You can visualize it here. That's what a dress looks like. That's a coat. That's a t-shirt or top. This is a pullover. These are trousers. You got bag, shirt. This is a sample. I think I have all the classes here. Let's just look at all the classes. All right, so what we got. We got 2 ankle boots, just different than a boot, I guess. Okay, so we have ankle boots, bags, coats, dresses, pullovers, sandals, shirts, sneakers, t-shirt and tops, trousers. Those are the kinds of images I have. In what space does this data live? How many dimensions? All right, how many dimensions is my data? So I have 5,000 images, and each image is 28 by 28. That's a tensor. I don't even know how to deal with this. 5,000 images, 28 by 28, so each image is a matrix. First thing I'm going to do is reshape this. I'm going to unroll those matrices, take all the columns and just take the column, stack it, take the next column, stack it. So I now have 5,000 images, and each image is now a 784-dimensional vector. That's going to be tough to visualize. How many dimensions is this data? Well, what's the intrinsic dimension of this data? Conceptually, I have 10 classes of things. So maybe it would be nice if the intrinsic dimension was like 10. Possibly boots have different styles. Maybe the boots have like 2 intrinsic dimensions. There's like clutches and different purses. And so maybe there's like 2 dimensions for purses, and dress have like A-line and not A-line and all that stuff. So maybe a bunch of dimensions for dresses too. So it's probably not 784, but it's probably still pretty high dimension. But I only have 2 dimensions and sometimes 3 on my screen. So let's see what we can do with this data. And also let's see what that scree plot looks like. Step 1, we're going to do SVD, subtract off the mean. I already normalized these pixels because pixels are all roughly the same units of brightness, so I'm not going to worry about that. I'm going to run this time scikit-learns principal component library. This is the same as running SVD, but I'm going to use the scikit-learn package. I don't technically need to subtract off the mean. It will do it for me anyways. This makes it a little easier, so I'm showing you again another way to do it. In practice, by the way, just do this. So when people reading your code are like, what is this SVD? Because they didn't take this class. They'll go, I don't know what that is. But they'll see, oh, PCA, I took the easy version of this class. I know what PCA is. That's dimensionality reduction. I can read your code. So you just fit some 50 dimensions to my data. Boom, that was quick. Let's look at our scree plot. Okay, so we need some more dimensions this time. Pretty good at the first few. I'd say maybe around 10. It does start to taper off. Certainly the rest of these don't do much. Right? This is definitely higher dimensional data. US politics were depressing, just like one-dimensional. Here we've got rich structure. So I'm going to pull out the transformed data. So I fit the PCA model. Now I'm going to take those eigenvectors, which are stored in the PCA model, the principal components. I'm going to project my X onto them and just take the first 3 columns of X. Because remember, I actually saved 50 dimensions of eigenvectors just for fun a moment ago. I'm going to add column Z1, Z2, and Z3 to my images data frame. Show you what that looks like. So now I have these things. So I took all these crazy numbers and I have 3 principal components. Let's do this. I'm going to show you a scatter plot. It's cool. Is there structure? See some clustering. You don't know how to do clustering yet, but if we ran a clustering, I go, there's a cluster here maybe. A cluster here. There's something going on in this data. What would we like to do to make this more interesting? Let's attach the labels. You have these colors. I think the label here is the label. Let's change this real quickly. You have a class as a dimension here. Let's see, bags. These are bags. Okay. How can we improve this plot? Let's color it. Let's set the color to be the class. Let's change this to class 2. That's it. How do we get? There's something going on here. In 2 dimensions, we start to see some kind of structure. These orange things are all sneakers and sandals and ankle boots. Okay. They're all kind of together. Shoe-like things. Good. And bags. Bags are kind of like shoes, right? Same shape approximately. So bags are over here. What's going on here? Coats and pullovers and a sandal. That's confusing. Coats, pullovers, shirts. Feeling like shirt things. And then I guess over here we got to have some dresses, t-shirts, trousers. Okay, that was weird. That's down here. Okay, dresses and trousers. And then there's just lots of trousers down here. So we did find interesting structure in this really high dimensional data that we could actually visualize. Why stop there? We have 3 dimensions. You can look at it in 3 dimensions, see what this looks like. So we start to see in 3 dimensions even more structure. There's like this pile of, what is this pink stuff? Ankle boots over here, right? And then there's this pile of bag stuff here, right? That's pretty organized. And then there's this mess over here of all this stuff that was just hard to separate. Coats, t-shirts, dresses, pretty similar, right? So we did find interesting structure in this data. If I were playing with this data and I found, a shirt that's over here, or sorry, an ankle boot over here, I'd be like, that's an interesting ankle boot. I should go check that one out. Didn't live in the right space. So sometimes we might use this to find outliers. Where did things just didn't agree with the patterns we see in the reduced dimension representation? One thing you could ask is, what if I just projected, instead of on these eigenvectors, but on something, just a random vector? So make some random vectors, some normal vectors in 784 dimensions. It's just random noise. And project onto that. Is there structure? This is interesting. Would you say there's structure here? Did I get some clustering of my data? Think. I say you kind of got a little bit. It's not nearly as good. There's a little structure. This kind of hints at something that's sort of magic about these high dimensional spaces. It, again, out of the scope of this class, but if I start to take random vectors and throw my data at random vectors, I get enough random vectors, they also may recover some of this high dimensional structure in a low dimensional space. These random projections can also work. And that's actually a whole family of other techniques that are, again, out of scope for this class. That said, if you had to pick just 2 or just 3 vectors to project onto, which are the best 3 you could choose to minimize the squared loss? The first 3 eigenvectors of the covariance matrix, the first 3 principal components. So they're the best we've got, but there's some structure in these other random projections too. But if I had to pick 3, I pick these 3. Let me show you another method, because now you know about dimensionality reduction. You can go just pull up scikit-learn and look at all the advanced methods, and they work exactly the same way. They just take a lot of time to run. So TSNE, very trendy among the machine learning crowd these days, is another way of finding this low dimensional representation. This is a nonlinear method. It's going to try to preserve some statistical structure. And sometimes it finds a little bit more separated classes. Oh, messed that up. Sometimes you get a little bit more structure. Can't scroll on this one. Yeah, so we get some more structure in my data. Right, so it does spread things out, maybe a little bit better, not a whole lot better. When you're doing the analysis, I would encourage you to just start with PCA. 1, there's a reasonable chance that people you might talk to will understand what you're talking about. And 2, it works pretty well and gets you a good starting point. If you're like, I really want to cluster this crazy data and I want to bring it down to low dimensional space, maybe do a clustering afterwards, then maybe try some of the other techniques like TSNE. And there's independent component analysis, a whole bunch of other techniques you could apply to your data. And they all work the same rough way, just different loss functions. Looks like in 3 dimensions, you can see there's maybe a little better separation of our components with this more advanced technique. Still, it gets these things confused. It just seems like coats and t-shirts are hard to tell apart. That's probably true. Probably hard for a human to see the difference between those things. So finding a simple representation, they're likely to be close by each other. One thing you could try to do is look at a subset of the data. So here I'm looking at coats or pullovers and coats, which are pretty similar, right? Pullovers and coats look pretty similar. You could try to run a projection on a subset of your data, and now you maybe have a different set of axes to spread things out on. You get a little bit of additional spread if I just look at the subset, but not a whole lot. So in this case, it's not likely to help just because this data is hard. Right. Okay. One last thing. Should I model on top of these techniques? Should I take my high dimensional data, bring it to lower dimensions, and then run logistic regression, which you just learned? Should I do that? Is that going to help me? This is both a mathematical, a philosophical, and a technical question. It's kind of fun. So if I'm doing linear stuff like logistic regression or linear regression, least squares regression, and I apply this transformation first, I'm applying a linear transformation to my data, and then I'm applying another linear projection in my weight space. So I'm just reducing the space of vectors of models that I can consider. So this will not improve my ability to fit the data. But I might still want to do it because maybe it could speed up some of the algorithms that I'm using, find this lower dimensional space. It might be easier to explain. It might be a little bit more robust. So you might do it. I would say in practice, don't, unless you're using a special kind of technique that depends on things like independent directions, which we haven't covered in this class. So just to give that point, make it a little bit clearer, I'm going to fit a logistic regression model to my z's, which I think, how big was z's here? Z's. So my three-dimensional space. I'm just going to look at the training error, so my prediction accuracy on the original data. And if I run it again on the original X, the non-reduced dimension representation, it's going to be better or worse? Who says better? Who says worse? Who says I don't know? Oh, no one voted, so just vote for something. All right, better? Worse? So I took a high dimensional thing, I made it simpler, I threw away information, and then I'm trying to fit a model to this simpler thing. I got an accuracy. What if I kept all that information? I fit a model to that original thing. Better or worse? Let's see. Significantly better. My training accuracy is much better because I can fit the data better because there's more information. I didn't throw away any pixels. I didn't reduce things down to this simplified three-dimensional space. I kept all that rich structure. So that one bright pixel in the top corner of that one purse can now be used to figure out that that's a purse. Okay. So be careful with dimensionality reduction. It is a common pattern for people to try to simplify their data and then run regression on it. This might help with generalization performance, but again, it's a trade-off here. So you might be improving generalization, but at the expense of your ability to express complex phenomena. So my guidance would generally be just apply the machine learning technique directly, use other regularization methods, unless this is explicitly called for. All right, so we actually finished everything just on time. We'll see you Tuesday for clustering.